Spacetime geometry. In general relativity, gravity isn't a force but a manifestation of the curvature of spacetime. This curvature is determined by the distribution of mass and energy, as described by Einstein's field equations. Geodesics, these are the straightest possible paths that particles, including light, which follows null geodesics, take through curved spacetime. Time-like geodesics are paths of massive particles, while null geodesics are paths of massless particles like photons. Geodesic incompleteness, this is the central mathematical notion used by the Singularity Theorems to define a singularity. A spacetime is considered geodesically incomplete if there are geodesics, paths of observers or light rays, that cannot be extended indefinitely in proper time, for time-like geodesics, or affine parameter, for null geodesics. This implies that a particle following such a path would have its existence abruptly end or begin, signaling a breakdown in the spacetime structure itself. This is a more rigorous way to define a singularity than simply stating it's a point of infinite density or curvature, as the singularity itself isn't part of the smooth spacetime manifold. Causal structure, this refers to the network of cause and effect relationships in spacetime. It's determined by the behavior of light cones, which define the future and past directions an event can influence or be influenced by. Energy conditions, these are physically reasonable assumptions about the nature of matter and energy. They essentially state that energy density should be non-negative and that gravity is attractive. Different theorems use different energy conditions. Null energy condition, NEC for any null vector k. A. T. AB. K. A. K. B. Greater than or equal to 0, where T. AB is the energy momentum tensor. This implies that the energy density experienced by a light ray is non-negative. Weak energy condition, WEC for any time-like vector v. A. T. AB. V. A. V. B. Greater than or equal to 0. This means that any observer measures a non-negative energy density. The WEC implies the NEC. Strong energy condition, SEC for any time-like vector v. A. T. AB. 2. 1. TG. AB. V. A. V. B. Greater than or equal to 0, where T is the trace of the energy momentum tensor and G. AB is the metric tensor. This is a stronger condition and essentially implies that gravity is always attractive. Some forms of matter, like a cosmological constant or certain scalar fields, e.g., inflaton fields, can violate the SEC. Dominant energy condition, December. In addition to the WEC, it states that for any future point in causal vector v. A. The vector T. AB. V. B. is also future pointing and causal. This means that the speed of energy flow cannot exceed the speed of light. Trapped surfaces. A crucial concept introduced by Penrose. A closed trapped surface is a closed, two-dimensional space-like surface where both outgoing and ingoing families of light rays orthogonal to the surface are converging, i.e., their cross-sectional area decreases. This indicates that gravity is so strong within this region that even light cannot escape outwards, it's pulled inwards. The existence of a trapped surface is a key indicator that gravitational collapse has become irreversible. The structure of singularity theorems. Most singularity theorems share a common logical structure. They typically require three main ingredients: an energy condition, an assumption about the properties of matter and energy, e.g., NEC, WEC, or SEC. A condition on the global structure of spacetime. This might involve assumptions about causality, e.g., the absence of closed time-like curves. Or the existence of a Cauchy surface, a space-like hypersurface that is intersected exactly once by every inextendable time-like curve, ensuring predictability. For example, Penroses theorem requires a non-compact Cauchy surface. The presence of strong gravitational fields, this is often signaled by the existence of a trapped surface, for black hole formation, or a sufficiently high density of matter in the past for cosmological singularities. If these conditions are met, the theorem concludes that the spacetime must be geodesically incomplete. Major singularity theorems and their implications. 1. Penroses Singularity Theorem, 1965. Focus: gravitational collapse and black hole formation. Key conditions. The null energy condition holds. The spacetime possesses a non-compact Cauchy surface. A closed trapped surface exists. Conclusion: the spacetime contains at least one incomplete null geodesic. Significance: this was the first of the modern singularity theorems. It showed that if a sufficiently massive star collapses to form a trapped surface, a singularity is inevitable, regardless of the symmetries of the collapse. This provided strong theoretical support for the physical reality of black holes and their singular nature. Roger Penrose was awarded the Nobel Prize in Physics in 2020 for this work. 2. Hawking's Singularity Theorem and Hawking-Penrose Theorems. Hawking, often in collaboration with Penrose, extended these ideas to cosmology and refined the conditions for singularities. Focus: cosmological singularities, like the Big Bang and black holes. Key conditions can vary between specific theorems. An energy condition, often the strong energy condition for cosmological theorems, or the weak and null energy condition for black hole theorems. A causality condition, e.g., no closed time-like curves. A condition indicating that gravity is sufficiently strong, such as the universe being closed and expanding, or the existence of a trapped surface. For instance, one version states that if the strong energy condition holds, there's no Cauchy surface, and the universe is expanding on average, measured by the divergence of a congruence of time-like geodesics, then there must have been a past singularity, the Big Bang. Conclusion: the spacetime is time-like or null geodesically incomplete. Significance. Big Bang, Hawking's theorems provided strong evidence that, under classical general relativity, the universe must have originated from a singularity, the Big Bang, where density and curvature were infinite. This meant that going backward in time, the paths of all matter and light would converge to a point of infinite density. Black holes. These theorems reinforced the idea that singularities are generic features within black holes, not just artifacts of specific solutions. What the singularity theorems mean and don't mean. Prediction of breakdown. The theorems predict that under physically reasonable conditions, Einstein's theory of general relativity itself breaks down at singularities. The infinite densities and curvatures signal that general relativity is no longer a complete description of gravity in these extreme regimes. Need for quantum gravity. This breakdown is widely interpreted as a pointer to the need for a more fundamental theory of quantum gravity, which would presumably resolve these singularities and describe the physics of the very early universe and the centers of black holes. Not necessarily points of infinite density, while often visualized as a point, a singularity, as defined by geodesic incompleteness, is more precisely a boundary or edge to spacetime where the laws of physics as we know them cease to apply. The geometrical structure can be more complex than a simple point, e.g., a ring singularity in a Kerr black hole. Cosmic censorship hypothesis. The singularity theorems predict the existence of singularities but don't necessarily say whether they are naked, visible to external observers, or hidden behind an event horizon, as in a black hole. The weak cosmic censorship hypothesis, proposed by Penrose, conjectures that all singularities formed from generic gravitational collapse are hidden within event horizons. This is a crucial, yet unproven, hypothesis in general relativity. If naked singularities could exist, they would pose significant problems for predictability in physics. Types of singularities. While the theorems prove geodesic incompleteness, the character of the singularity can differ. Space-like singularities. The singularity lies in the future, e.g., inside a Schwarzschild black hole, or past, e.g., the Big Bang, of all events in a certain region. Observers inevitably hit it. Time-like singularities. These are singularities that could, in principle, be avoided by an observer because they do not necessarily lie in the future of all events. These are less common in known solutions. Null singularities. These occur on light-like surfaces. An example could be the Cauchy horizon inside a charged or rotating black hole. Singularities can also be characterized by their strength. Strong singularities, tidal forces become infinite, destroying any object approaching them. Weak singularities, tidal forces might not be infinite, but the laws of physics still break down. The null energy condition states that for any future-pointing null vector k, mu, the contraction of the energy momentum tensor T, with this null vector must be non-negative. T, k, mu, k, nu, greater than or equal to 0. Energy momentum tensor, T. This tensor is a central object in general relativity. It describes the density and flux of energy and momentum in spacetime. Its components represent T, 0, 0. Energy density, T, 0, I. Energy flux, momentum density in the ith direction, T, I, 0. Momentum density in the ith direction, same as T, 0, I. For symmetric tensors, T, Ij. Stress, pressure and shear stress, in the ith and jth directions, indices 0 usually refer to the time component, and ij refer to spatial components. Null vector, k, mu. A null vector is a vector whose length in spacetime is 0. Mathematically, if G is the metric tensor, then for a null vector k, mu, we have G, k, mu, k, nu, equals 0. Physically, null vectors represent the paths of massless particles, such as photons, light rays. Future pointing means the vector is directed towards the future light cone. In simpler terms, the NEC asserts that the energy density as measured by an observer moving at the speed of light, a light ray, is never negative. Physical interpretation. The physical interpretation of T, k, mu, k, nu, can be understood as follows. If k, mu, is the tangent vector to a congruence of null geodesics, a family of light rays, then T, k, mu, k, nu, is related to the energy density encountered by these light rays. The NEC essentially imposes the condition that gravity, when acting on light rays, is generally attractive, or at least not repulsive enough to cause them to diverge uncontrollably without some exotic form of matter or energy. Connection to Raycorie's equation. The NEC significance is deeply tied to Raycorie's equation, which describes the evolution of the expansion, theta, of a congruence of geodesics, either timelike or null. For a congruence of null geodesics with tangent vector k, mu, Raycorie's equation takes the form d equals 2, 1, theta, 2, sigma plus omega r k mu k nu, where lambda is an affine parameter along the geodesics. Theta is the expansion, rate of change of the cross-sectional area. Sigma is the shear tensor, measuring distortion in shape. Omega is the vorticity tensor, measuring rotation, often 0 for surface orthogonal geodesics. R is the Ricci curvature tensor, which is related to the energy momentum tensor T. Through Einstein's field equations, R 2, 1, Rg equals C 4, 8G T. Using Einstein's field equations, we can substitute for R K mu K nu R K mu K nu equals C 4, 8G T 2 1. Tg k mu k nu. Since k mu is a null vector, g k mu k nu equals 0. Thus, the equation simplifies to r k mu k nu equals c 4 8g t k mu k nu. So, Récaury's equation for null geodesics becomes d equals 2 1 theta 2 sigma plus omega c 4 8g t k mu k nu if the null energy condition T k mu k nu greater than or equal to 0 holds, and if the vorticity is 0, which is often the case for congruences relevant to trapped surfaces, then the term C 4 8g t k mu k nu is non-positive. The terms 2 1 theta 2 and sigma are also non-positive, since sigma is a sum of squares. This means that if the NEC holds, gravity tends to make d negative, implying that gravity focuses null geodesics, light rays, causing them to converge. This focusing effect is a key ingredient in the formation of singularities. If light rays converge, their cross-sectional area decreases, potentially leading to a point where the area becomes 0, a caustic or a focal point, which can signal a singularity. Relationship to other energy conditions. The NEC is implied by several stronger energy conditions. Weak energy condition, WECT. V mu V nu greater than or equal to 0 for any time-like vector v mu. This means the energy density measured by any physical observer is non-negative. Since a null vector can be seen as a limit of time-like vectors, the WEC implies the NEC. Dominant energy condition, December states that the WEC holds, and additionally, the vector T v nu is future-pointing and causal for any future-pointing causal vector v mu. This means that energy momentum can never be observed to flow faster than light. The December implies the WEC and therefore the NEC. Strong energy condition, sec. T 2 1 Tg v mu v nu greater than or equal to 0 for any time-like vector v mu. This sec implies the NEC for normal matter where the trace T of the energy momentum tensor isn't too large and positive, though there are edge cases. The sec is a stronger statement about the attractive nature of gravity for time-like geodesics. The NEC is the weakest in the sense that if it is violated, typically the WEC and December are also violated. Matter energy fields and the NEC. Fields that typically satisfy the NEC. Scalar fields with standard kinetic terms and non-negative potentials, for a scalar field phi with Lagrangian L equals 2 1 del mu phi v phi. The NEC is satisfied if v phi is non-negative or not too negative. Most ordinary matter fields, like those in the Standard Model, excluding certain quantum effects, generally satisfy the NEC. Electromagnetic fields, an electromagnetic field satisfies the NEC. perfect fluids with ρ plus p greater than or equal to 0. For a perfect fluid with energy density ρ and pressure p, the NEC requires ρ plus p greater than or equal to 0. Most ordinary fluids satisfy this, e.g., dust has p equals 0 ρ greater than or equal to 0, radiation has p equals ρ3 ρ greater than or equal to 0. Fields or situations that can violate the NEC. Classical scalar fields with negative kinetic energy, phantom fields if a scalar field has a wrong-signed kinetic term, rel equals plus 2, 1, del, mu, del, mu, phi v, phi, it will generally violate the NEC. Such fields are often considered exotic. Certain modified gravity theories. Some modifications to general relativity can be formulated in a way that an effective energy-momentum tensor, containing terms from the modified gravitational sector, violates the NEC. Quantum effects, this is the most physically relevant area where NEC violations can occur. Casimir effect, the vacuum energy between two closely spaced conducting plates can be negative, leading to a local violation of energy conditions, including the NEC under certain interpretations or for effective descriptions. Hawking radiation, the region near a black hole event horizon, due to quantum particle creation, can have a flux of negative energy flowing into the black hole, which can be interpreted as a violation of the NEC. Inflationary cosmology, some models of cosmic inflation, particularly those involving certain types of scalar fields, inflatons, may require a temporary violation of the strong energy condition. While the NEC itself might not always be violated during inflation, very rapid acceleration, superinflation or phantom expansion where h0 would necessitate NEC violation. Higher derivative theories, theories of gravity or matter involving higher-order derivatives in their Lagrangians can sometimes lead to NEC violations. It's important to note that pointwise energy conditions like the NEC are statements about classical general relativity. In the context of quantum field theory, it's known that all pointwise energy conditions can be violated locally by certain quantum states. This has led to the development of averaged energy conditions, such as the averaged null energy condition, ANEC, which states that the integral of T k mu k nu along an entire null geodesic is non-negative. The ANEC is thought to be more robust and has been proven for certain quantum fields in various spacetimes. Significance of the null energy condition. Singularity theorems. The NEC is a crucial assumption in Penrose's original singularity theorem, which demonstrates that gravitational collapse to a trapped surface inevitably leads to a singularity, geodesic incompleteness for null geodesics. Many other singularity theorems, including some by Hawking, also rely on the NEC or conditions that imply it. The fact that such a minimal energy condition is sufficient to predict singularities underscores how generic these features are within classical general relativity. Black hole physics. Area theorem, Hawking's area theorem, which states that the area of a black hole's event horizon can never decrease, classically, relies on the NEC. Violations of the NEC could, in principle, allow the event horizon area to shrink. Cosmic censorship, the NEC is often invoked in discussions and attempts to prove the cosmic censorship hypotheses, which conjecture that singularities formed from gravitational collapse are always hidden behind event horizons. Wormholes and time machines. Traversable wormholes, standard general relativity solutions for traversable Morris-Thorne wormholes, hypothetical tunnels connecting distant regions of spacetime, require the presence of exotic matter that violates the null energy condition at the wormhole throat. This is because the flaring out condition for the wormhole geometry, light rays diverging from the throat, necessitates r k mu k nu 0, which in turn implies T k mu k nu 0. Time machines, the construction of certain types of time machines, allowing for closed time-like curves, in general relativity often also requires NEC violating matter. Bouncing cosmologies, cosmological models that propose a bounce instead of a Big Bang singularity, where a contracting universe transitions to an expanding one, generally require a violation of the NEC, or conditions that imply it, like the sec, around the bounce phase. This is because the focusing tendency of gravity, guaranteed by the NEC, would normally lead to a singularity. That was all. Goodbye.